Today we're going to continue our discussion of the electron and how important it is in chemistry. We're going to start talking about electron configurations and what they actually tell us today. But first, let's define that. Electron configurations actually show where the electrons will be found. In our periodic table, you're going to find the electron configuration below the symbol and underneath the atomic number. What this electron configuration is telling us is the first principal energy level has 2 electrons, the second has 8, the third has 18, the fourth has 18, the fifth has 8, and the sixth has 2 electrons. So each of those numbers is actually separated by principal energy levels. So that'll actually give you a lot of information. Knowing now how the electrons fill into each of the principal energy levels, you know that the 4s fills before the 3d. And because we have our electron configuration given like this, you don't actually need to know that. You can still figure out where all the electrons are. They're already separated into their proper principal energy levels. So the electron configuration is separated by the PELs. You might want to take a second and write out principal energy level in case you've forgotten what that is or might forget when you look later. So we're going to talk about how to create an orbital notation now. But before we can do that, let's talk about a couple of rules that you need to follow in order to figure this out. The first one we call the bus seat rule. If you were getting on a public bus and there were people sitting by themselves in some seats and there were some open seats, you would not sit next to somebody as long as there was still an open seat. And we call it the bus seat rule because it's like that. If an electron is sitting in a seat, but there's an open seat, the new electron will actually go and sit in the open seat. They won't sit with another electron unless they're forced to. So we're going to say each orbital gets 1 electron until all are filled. Okay, so we'll show you how this is all denoted in a second. You can kind of see it underneath here, but let's finish these 2 rules. The other rule is the electron spin. If you think about it, you're trying to put 2 negative charges in the same space, the same volume, the same area. And putting 2 electrons in the same area with the same charge, it's going to create some repulsion. So in order to compensate for that, they're actually spinning in opposite directions. And when they spin in opposite directions, they kind of take on an opposite, not opposite charge, but their charges don't have a chance to repel each other as much. So the electrons are actually spinning in opposite directions. So the notation we're going to learn today is called the orbital notation, is going to need to reflect both of these rules, this bus seat rule and this electron spin rule. So if you look off to the right here, I have a little diagram sort of showing you everything that we're going to include in an orbital notation. The number that's given in the notation here, that's going to tell you the principal energy level. The letter next to it, in this case the S, is telling us the sublevel. This line, this horizontal line, is actually telling us how many orbitals we have. There's only 1 line for S. If you look over here to the left, there's 3 lines for P. If I was drawing D, there would be 5, and for F, there would be 7. So memorizing that little chart from the notes yesterday is really going to help you, and there's no reason why you can't jot it down on the page when you are doing orbital notation. So this line is going to represent the orbital. And then the two arrows represent the electrons. Note that one is going up and one is going down because those electrons are going to spin in opposite directions. So those are our electrons. All right, so we're going to attempt to draw the orbital notation for sodium. So in order to do that, we're going to need the electron configuration. We used to have to do this just based on the atomic number. Now we get this, which makes our lives a lot easier. So let's pull up our periodic table. So here's our periodic table. We need to find sodium. Now if you need to look in table S in order to find out which element sodium is, please do so. It is not S. S is sulfur. Sodium is Na right here, and its electron configuration is 281. I'm going to jot that down over here so that I can use that when making my orbital notation. Now I'm going to just sweep this out of the way. So my electron configuration is telling me I have 2 electrons in the first principal energy level. I've helped you out by starting your orbital notation this time. You're going to have to create this yourself eventually. So in the first principal energy level, and we always start with S. In fact, why don't I write that out too? S, P, D, F, 1, 3, 5, 7. That tells me how many orbitals in each of the sublevels. So S has 1 orbital, and so there's 1 line. I need to put in both electrons, so we're going to draw 1 arrow up, 1 arrow down. A lot of chemists will actually draw the arrows like this with only 1 head because it's a little less, or 1 side to the head, to make it a little less messy. That's how my chemistry professors always did it, so that's how you'll see me draw it. You can, however, draw it with the full head on the arrow. Just kind of try to be careful, don't make it too messy that we can't tell what you're doing. All right, so now we have actually placed all the electrons in the first principal energy level. I'm also a bit of a list maker, so I like crossing things off as I do it. So in the second principal energy level, we have to place 8 electrons. Once again, we need to start with S, which has 1 orbital. So you see the 1 horizontal line. It can only fit 2 of those 8 electrons. I still have 6 more to place, so I'm going to need P, which has 3 orbitals. So you'll see I've drawn P with 3 horizontal lines. When we fill these, we have to keep in mind the bus seat rule. We're going to fill them one at a time before we go back and fill in the second one. So we have 1, 1, 1, and then we put in this second. Will I know if you filled it in that way? No, since we used all 6 spots for the electrons, I wouldn't know that. But it's best to get in that habit so you don't accidentally do it wrong and lose points. So now I have placed all 8 electrons, 2, 4, 6, 8, in my second principal energy level. So I'm done with my second, and I can move on to the third principal energy level, where I only need to place 1 electron. Again, I'm going to start with S, which only has 1 orbital, and I'm going to put in my 1 electron. Normally, I wouldn't have even drawn this, but we put them all in just in case. So I am now done drawing my orbital notation for sodium. Let's try another one. We're going to do it for phosphorus this time. So let's find phosphorus. Phosphorus is over here. Its electron configuration is 285. Get that out of the way, and we'll record that. 285. Well, now I can't see my little cheat sheet, so I'm going to do that here. SPDF 1, 3, 5, 7. All right. So for phosphorus, we have 2 electrons in the first. We always start with S, So 1 for the principal energy level, S for the sublevel, and S has just one orbital, so I'm going to put in one horizontal line. I'm going to place my 2 electrons, and I'm now done with the first principal energy level. Now in the second principal energy level, I have 8 electrons. Once again, I'm going to start with S. This time it's in the second principal energy level, which has just one orbital, so one horizontal line, and then can only fit 2 electrons. I still have 6 more to place, so I'm going to have to move on to P, which has 3 orbitals. So I have 2p, 1, 2, 3, and in each of those we're going to fill in. This is electron 1, electron 2, 3, 4, 5, 6, 7, 8. Now I've placed all 8 in the second principal energy level. So I'm going to move on to the third. We always start with S, which has 1 orbital. I'm going to skip over here a little bit because I made my cheat sheet too big. And it can hold 2 electrons. But I have 5, so I'm going to need to move on to P, which has 3 orbitals. 3p, 1, 2, 3. I've already placed 2 electrons in the third, 1, 2, 3, 4, 5. Now you can see why it's important to always follow the bus seat rule. If I had just been filling the orbitals with 2 each time, you wouldn't have had these 3 electrons sitting unpaired like that. And the number of unpaired electrons becomes really important when we get into bonding. So really important that you know to fill them one at a time. All right, let's try another one. We're going to try silicon. Silicon is here, and its electron configuration is 284. Put that up here. All right, once again, we start with the first principal energy level, which only has S, which only has 1 orbital. It can fit 2 electrons, and I'm done with the first. Now we're on to the second. Always start with S, which has 1 orbital. We can fit 2, but we still have 6 more electrons, so I must need to move on to P, which has 3. 1, 2, 3. We've already placed 2 electrons, 3, 4, 5, 6, 7, 8. Now I've placed all 8 in the second principal energy level. I need to move on to the third. We always start with S, which has 1 orbital and can fit 2 electrons. I still have 2 more to place since I started with 4, so I'm going to move on to P, which has 3 orbitals. Even when you know you're not going to use all 3 orbitals, make sure you draw all 3. So we have 2 more to place, so this is 3 and 4. And that's how you draw it for silicon. We'll do one more together. Magnesium is right here, and its electron configuration is 282. 282. We always start with the first, which always starts with S, which always has 1. And we can fill in 2 electrons. Done with that. On to the second, always start with S, which has 1 and can hold 2 electrons. But we have 6 more to place. So we move on to P, which has 3 orbitals. 3, 4, 5, 6, 7, 8. Now we've placed all 8 of those. So we move on to the third principal energy level. We start with S, which can hold 2. And that's actually it for magnesium. Hopefully that's enough practice. We'll do some more in class together. Next, we're going to talk about the different experiments actually that Bohr had done and figured out that electrons seem to have very specific energy that they absorbed and released. So when he did that, he described something we now call the bright line spectra. What you're looking at on the left is an example of a helium atom in the ground state. The ground state means that it has, those electrons have the lowest energy possible. And you'll notice that they are in the first principal energy level, which can hold 2 electrons. And that's how many electrons helium has. So that's in the ground state. What could happen is that energy could be absorbed by those electrons. So if we get this all excited and have it absorb some energy, those electrons will actually jump up to higher energy levels. There's a few different ways you can excite electrons. You can do it by fire, you can do it with electricity, and then what will actually happen is they'll jump up to a higher energy level. But just like when you drink an ice cap or something and all of a sudden you're all wired with sugar and caffeine, you can't stay that way very long and you'll crash and you'll go back down to your original energy state, or in some cases lower, but that doesn't happen with electrons. So when they come back down to their lower energy state, they have to release that energy. And they actually release it in the form of light. So you may get blue light from that electron, but you might get some pretty purple or something from this other electron. So you're going to get these very specific colors as a result of the loss of that energy. So a bright line spectrum is colors given off by an element. And they are very specific. We can actually identify an element based on its bright line spectrum. It's kind of like the fingerprint of elements. So every element has its own bright line spectrum. And it's kind of like a fingerprint. We can use it to identify the element. So light is actually made when electrons fall back to the ground state from the excited state. Notice that when I drew in these colors that were emitted, I did it based on when it fell back to the ground state. So really important that you understand that. Light is made when electrons fall back to the ground state. All right. So if we look below, we would ideally have these in color. So these are actually bright line spectra, and what you're seeing are the different wavelengths of light that would have been emitted by that element when those excited electrons fall back to the ground state. So these are the bright line spectra of 3 different elements, and down here we have a sample, which may have 1 or 2 or 3 or whatever many of those elements in it. And really all you're going to do is match up the banding or match up the bright line spectra to find out which elements are actually in there. And you may be doing that right now as you look at mine. And you can see that some of them are lining up. You'll see that this and this are lining up with these 2, which also means that this is from that one, and this one, and this one, and this one, and so on. So we definitely have element 2 in there, but there were some bands in this that did not line up. So where did these other ones come from? So you can match those up. Actually, it looks like it's element 3. Let's go ahead and define ground and excited state. Ground state is when the electrons are in the lowest energy possible. I'm going to say energy levels possible. And then excited state is when one or more electrons have absorbed energy, and that could be by fire or electricity, and have jumped up to a higher energy level. All right, so let's do a little practice with the information we learned today. We're also going to need our reference tables, specifically the periodic table, and you may also need table S. All right, so I have my periodic table. They're asking for the electron configuration of magnesium. I see often students confuse electron configuration and orbital notation. The electron configuration is labeled in the key in the center of your periodic table, so maybe you won't confuse that so much. So magnesium is actually Mg, which is number 12, and they've given the electron configuration to be 282. All right. Next question, the orbital notation for carbon. We know that it's kind of hard to figure out the orbital notation without the electron configuration, so we're going to record that first. It's right here, 2-4, and now we can figure out our orbital notation. I'm going to do my little cheat over here, SPDF, some people do fine, and then odd numbers, 1, 3, 5, 7. All right, so we're going to start with the first principal energy level, which we always start with S, which has one orbital or one horizontal line and can hold 2 electrons. We're done with the first. Now we're going to do the second, always start with S, one orbital can hold 2 electrons. But we're not done because we still have 2 more electrons to place. So we move on to P, which has 3 orbitals. 1, 2, 3. So we place 2, we need to place 3 and 4, and we're done. All right, next we're looking for the orbital notation of argon. Argon is a noble gas, it's over here, and its electron configuration is 288. So that's helpful when we're doing this. We start with the first, S, fill in our 2 electrons. We're done with the first principal energy level. We can move to the second, again starting with S, 2 electrons. We still have 6 more to place, so we're going to move on to P, which has 3 orbitals. And that's 3, 4, 5, 6, 7, and all 8 in the second are placed. We can move on to the third, again starting with S, 2 electrons, but we still need to place 6 more, so we need P, 3, 4, 5, 6, 7, 8, and we're done with that. Number 4, why are the arrows in the same orbital opposite each other? They're asking why do we have them spinning opposite? Because the electrons spin in opposite directions. They couldn't exist in that same space if they weren't. All right, circle the words that make the statement below correct. So we're ending here with ground state. So light is emitted when electrons fall back to the ground state. That's how light is produced. Now this we haven't really talked about, so let's look at this. The electron configuration for each of the elements in the periodic table is given in the ground state. So if you compare the electron configuration here to the one in the periodic table, as long as there's the same number of electrons, they could theoretically give you an ion, which would have 1 more or 1 less or 2 or 3 or whatever. but if it adds up to the right number of electrons, but it doesn't look the same, this is going to be excited. So if you look at germanium, we have 2, 8, 18, 4, but over here we have 2, 8, 17, 5. So what happened was one of the electrons with that 18 in the third principal energy level must have jumped up to the fourth. So this one's actually excited. And then we can look at sulfur. Sulfur right here we have 1, 8, 6, 1, and over here 2, 8, 6. So one from the first principal energy level must have jumped up to the fourth. So that one is also excited. Now this next one might look excited, but I have a feeling it's not. Vanadium 2, 8, 11, 2. So that one's actually ground state. Sodium, here's sodium, it should be 2, 8, 1. This is 2, 7, 2, so one from here jumped up to there. And then arsenic, we have, arsenic, which is here. It should be 2, 8, 18, 5, so that's ground state. And calcium 2, 8, 8, 2, which is what it is here. So none of those were ions, but some were excited. And the ones that were excited were germanium, sulfur, sodium, and I think that was it. So just keep in mind that the electron configuration in the periodic table is always in the ground state. All right, next question. Write the electron configuration for aluminum if one of the electrons in the second principal energy level jumped up to the fourth. So let's look at what aluminum normally is. It's 283. Switch back to black. So they want one from here to jump up to the fourth. So it's going to end up being 2, 7, 3, 1. So all I did was take one from this 8, making this 7, and I put it up into the fourth, which didn't exist before. What is the bus seat rule? Electrons fill one at a time before pairing. All right, and then this last one, how many unpaired electrons are in a ground state atom of phosphorus? We didn't happen to draw phosphorus, did we? I feel like we did, maybe back another page. So phosphorus is 285. So we kind of have to draw the orbital notation to figure this out. 1s is full. 2s, 2p. I'm going pretty fast here. Hopefully you're following along. That's the 8. Then 3s, there's 2. And then 3p, 3, 4, 5. Unpaired electrons are electrons that are sitting by themselves on the bus, and those are going to become more significant when we talk about bonding. And that's it for today, but we're not done talking about electrons. We won't be till the end of the year.